In exercise number 1, determine if W, which is 1, 3, minus 4, is in null A. We said that every vector is in null A if we multiply that vector by the matrix A and we get 0. So now let us check what is AW. So AW is equal the matrix A, 3, 6, minus 8, minus 5, minus 2, 4, minus 3, 0, 1, and we multiplied by the vector 1, 3, minus 4. So the result will be 3 multiplied by 1, minus 5 multiplied by 3, minus 3 multiplied by minus 4, then 6 multiplied by 1, minus 2 multiplied by 3, 0 multiplied by minus 4, then minus 8 multiplied by 1, 4 multiplied by 3, then 1 multiplied by minus 4. This will give us 0, 0, 0. So since AW is equal to 0, then W is in null A. So W is in null A. In exercises 3 to 6, find an explicit description of null A by listing vectors that span the null space. So we want to find the explicit description of null A. That means we want to find all the vector x such that AX is equal to 0. So let us do number 3. So we'll solve A0. We want to make this one in reduced echelon form. 0, minus 2, then 0, 0. So if we do one row operation, which is row 1 is equal minus 3, row 2 plus row 1, we get our new matrix will be 1, 0, 0, 1, then here minus 7, 6, 0. This one is 4, minus 2, 0. So here we have x1, this one is x2, x3, x4. So from here x1 will be equal 7 x3 minus 6 x4, x2 will be equal minus 4 x3 plus 2 x4, then x3 will be a free variable, so this is x3, x4 is equal to x4, which is also a free variable. So from here x will be equal x1, x2, x3, x4. So this will give us. So for x1, x2, x3, x4, we see here we have two free variables, which is x3 and x4. So we can write this one as x3 multiplied by a vector plus x4 multiplied by a vector also. So we will take the coefficients of x3, which is 7 minus 4, 1, 0. The coefficients of x4 is minus 6, 2, 0, 1. So the spanning set for the null A is the two vectors, which is this one and this one. If we say this one is v1, this one is v2. So spanning set for null A is equal v1, v2, which is the vector minus 7 minus 4, 1, 0 and minus 6, 2, 0, 1. Similarly, we will do number 5 in the same way we did exercise 3, and we get here the spanning set. The spanning set for 5, from here we'll get x will be equal x1, x2, x3, x4, x5. So this will be equal. You will find here we have also two free variables, which is x2 and x4. So the free variables will be x2 and x4. So write this one as x2 multiplied by the coefficients of x2 plus x4 multiplied by the coefficients of x4. After you rewrite this one as this form, you will find that the coefficient of x2 will be 2, 1, 0, 0, 0. The coefficients of x4, you will find it minus 4, 0, 9, 1, 0. So you can conclude that the spanning set of null A is equal, if we said also this one is V1, this one is V2, is equal V1, V2. In exercises 7 to 13, either use an appropriate theorem to show that the given set W is a vector space, or find a specific example to the contrary. So the first one we have A, B, C, where A plus B plus C is equal to 2. This one, it is a subset of R3. So if we say this one is W, so 7, W is a subset of R3. But is the 0 vector is inside W, we said that A plus B plus C should be equal to 2. We cannot substitute here 0, 0, 0 to get 0 is equal to 2 because 0 is not equal to 2. So from here we say that the 0 vector is not in W because we cannot substitute all of them 0. We get 0 is equal to 2. This is incorrect. So the 0 vector is not in W, hence W is not a vector space. Now for number 9, we have W is equal A, B, C, D, where A minus 2B is equal 4C, 2A is equal C plus 3D. We can rewrite this one, W is equal A, B, C, D, where A minus 2B minus 4C is equal to 0, and 2A minus C minus 3D is equal to 0. This is a homogeneous system. We can also rewrite it as it is equal to span of, if we take the coefficients of A will be 1, 2, the coefficients of B will be minus 2, 0, the coefficients of C will be minus 4, minus 1, the coefficients of D is 0, minus 3. So W is equal span of these three vectors. We know that if we have a span, we can rewrite the set as a span of vectors. This is by theorem 1, it is a vector space. Or because it is a homogeneous system, we said that every homogeneous system we can represent it as a null A. So that means it is a subspace or a vector space. So thus from here W is equal to null A, where A, our matrix A, we can represent as the vector of this one, which is 1, 2, minus 2, 0, minus 4, minus 1, 0, minus 3. And W is a subspace of R4 by theorem 2, and it is a vector space. So W is a subspace of R4, hence W is a vector space. vector space. So then for number 11, for 9, either you use it is a null space, so that means it is a homogeneous system, so that is by theorem 2 it is a vector space, or you use it is a span of 4 vectors, so using theorem 1, so it is a vector space also. For 11, if we write also this one is W similarly, so W is equal, if we write it as, for example, if we take P, so here we have 1 0 1 0 plus then D, which is -2 1 3 1 plus the vector 0 5 0 0. So if you see this one, it does not contain the 0 vector, because if we make this one to be 0, this one to be 0, we have 0 5 0 0, which is not inside W, which is not the 0 vector. You cannot find a 0 vector for this one, which is combination of this vector plus this one plus this one. So because the 0 vector, it is not inside W, we conclude that this one is not a vector space. It is clear that W is a subset of R4, but W does not contain the 0 vector. Or let us say 0 vector is not inside W. Since this 5 is here, so we cannot make this one to be 0. So the 0 vector is not in W, so hence W is not a vector space. Now for 13, we have C minus 6D, D, C, where C, D, it could be any real numbers. We can rewrite this one. It is clear for here, W is a subset of R3, and we can write W is equal C multiplied by 1 0 1 plus D multiplied by -6 1 0. So from here we can rewrite it as a matrix, or we can use also it is a span of 2 vectors, so that means it is a vector space or a subspace. Either which method you prefer, it will be all of them will be correct. So if we write this one as a matrix, so 1 0 1 -6 1 0, we have here C D. So W is equal col of A, which is the linear combination of the columns of the matrix A. Thus W is a subspace of R3 by theorem 3, and it is a vector space. So either method you use, all of them will be correct. Either you write it as a span of 2 vectors, either you write it as a col of A, either you write it as a null of A. So if we use this one, is W is equal col of A, where our matrix A is equal 1 0 1 -6 1 0. So thus W is a subspace of R3. So by theorem 3, W is a vector space. In 15, find A such that the given set is called A. So this is the call A. We want to find what is the matrix A. So we can rewrite this one. If we say this one is W, so we can rewrite W is equal to, we will take the coefficients of R, S, and T. So the coefficients of R are, we have 0, 1, 4, 3, plus the coefficients of S are 2, 1, 1, minus 1, plus the coefficients of T are 3, minus 2, 0, minus 1, where R, S, T are real numbers. So since the W is a set is of col A, that means it is the linear combination of the columns of the matrix A. So A will be equal, this one is just col A. So A will be the columns of 0, 1, 4, 3, 2, 1, 1, minus 1, 3, minus 2, 0, minus 1. So this is our matrix A, where the columns are 0, 1, 4, 3, 2, 1, 1, minus 1, 3, minus 2, 0, minus 1. For the matrices in exercise 17 and 19, A, find K such that null A is a subspace of Rk. B, find K such that col A is a subspace of Rk. We know that if we have our matrix A multiplied by X, this is equal to B. We know this one represent is col A, where this one represent null A, where B is equal to 0. Null A, where B here it is equal to 0. If our matrix is M by N, our X should be N by 1, and our B will be M by N. We said that col of A is equal, which is, sorry, this one is M by 1, not by N. We said that col of A will be in Rm, whereas null of A will be in Rn. So the first matrix in 17, we have our matrix A, it is 4 by 2. So part A, find K such that null A is a subspace of Rk. So null A will be equal R. We said null will be in Rn. So this is M by N, so null A will be R2, and col A will be equal Rm, which is R4. So similarly for 19, our matrix it is 2 by 5. So A is 2 by 5. That's mean null A is equal Rn. That's mean it is R5. B and col A is equal Rm, which is R2. In 21, with A as an exercise 17, find the non-zero vector in null A and a non-zero vector in col A. We know that a non-zero vector in null A is X such that Ax is equal to 0. And the non-zero vector in col A is any vector of the matrix A. Our matrix A is equal, according to exercise 17, it is 2, minus 1, minus 4, 3. Here we have minus 6, 3, 12, minus 9. So if we do row operation for this one, we will get it is equal to here 2 minus 6, then 0, 0, 0, 0, and 0, 0. So to find any vector, non-zero vector inside the matrix, inside the null A, that means we need to solve this one. So if we do one more row operation for this one, will be 1 minus 3, 0, 0, 0, 0, 0, 0. So from here it is clear that x1 is equal 3x2, x2 is equal x2, which is a free variable. So from here x will be equal x2, and here we have 3, 1. So any vector in null A should be in the form x2 multiplied by 3, 1. So null A is the span of the vector 3, 1. We need a non-zero vector 1. So if x2 is equal 1, the vector 3, 1 will be inside null A. You can choose any value for x2 multiplied by the vector 3, 1, so it will be in null A. For finding any vector in call A, just choose any vector, either the first one or the second one. So if we choose the first one, 2, minus 4, minus 1, minus 4, 3, this one is in call A. Similarly, in 22 or 23. So 22 is the same idea of 21. So now for 23, let A is equal minus 6 minus 3, 12, 6, and W is equal to 1. Determine if W is in call A, is W in null A. To know if W is in null A, just we need to multiply A by W. If this one is equal to 0, so W will be in null A. So let us check. A multiplied by W, this will give us minus 6 minus 3, 12, 6 multiplied by 2, 1. So this will give us minus 6 multiplied by 2 will be minus 12 plus 12. Minus 3 multiplied by 2 minus 6, and here we have 6. So this is equal to 0, 0. So since AW is equal to 0, then W is in null A. Now we want to check if AW is consistent, so that means W will be in call A. So AW, if we do row operation for this one, that means we have minus 6 minus 3, 12, 6, 2, 1. If this system is consistent, then that means W is a linear combination of the columns of A. That means it is W is in call A. If the system is inconsistent, that means W is not in call A because it is not a linear combinations. So after doing one row operation for this one, you will get this one is minus 6, 12, 2, then 0, 0, 0. So here, since the system is consistent, that means W is in call A. So since the system is consistent, then W is in call A. In 24, let A is this matrix, which is 3 by 3, W is 2, 1 minus 2. Determine if W is in call A, is W in null A. So in the same way we did exercise 23, we'll do also 4. So asking is W in call A, that means is the system AW consistent? Asking is W is in null A, similarly if we ask is AW is equal to 0. So let us check the first one, AW. We'll do row operation for this one. If the system consistent, that means our W is in call A. But if the system is not consistent, that means W is not in call A. Minus 2, 4, 0, minus 9, 8, 4. Here we have 2, 1, minus 2. So after doing row operation, we end up with this matrix 1 minus half, then 0, 1 half, 1, 0, 0, 0, 0. So it is clear here this matrix is consistent, this system is consistent, so W is in call A. since the system is consistent, then W is in call A. Now to check is W in null A, we want to find AW, so that's mean the matrix A multiplied by W. Two, 1 minus 2. If this one is equal to 0, that means it is yes, because this one is in null A. So minus 8 multiplied by 2, minus 2 multiplied by 1, minus 9 multiplied by minus 2. Then 6 multiplied by 2, 4 multiplied by 1, 8 multiplied by minus 2. 4 multiplied by 2 plus 0 multiplied by 1, 4 multiplied by minus 2. So this will give us here 0, 0, 0. So from here, W is in null A. In exercises 25 and 26, A denotes an M by N matrix. Mark each statement true or false, justify each answer. So the null space of A is the solution set of the equation AX is equal to 0. So this one is true because it is from the definition. We said that the null space is all solution of AX is equal to 0. So A is true. Now for B, the null space of an M by N matrix is in Rm. This one is false because we said it is Rn, because it is represent X, and X should be in Rn. The column space of A is the range of the mapping XAX. So the column space is the range of the mapping. We say this one also it is true because the call space is all the linear combination of the matrix A, and the range is all the mapping of X to AX. So this one is true. Now for D, if the equation AX is equal to B is consistent, then call A is Rm. This one is false because it should be consistent for every P to be in call A. So this one is false. AX is equal to B must be consistent for every V, for each V. So now E, the kernel of a linear transformation is a vector space. This one is true. Call A is the set of all vectors that can be written as AX for some X. This is from the definition, it is true. Just let us to write here the letters to not confuse. So this one for F. Now let us see exercise 26. Also it is true or false. So A null space is a vector space. We said this one is true. We see this one from the class. Then B, the column space of M by N matrix is in Rm. This one is also true because it represents the B. So C, call A is the set of all solution of AX is equal to B. This one it is true, but it is missed for some X in Rn. So this one is false. We need to add for some X. Then D, null A is the kernel of the mapping X to AX. This one is true. Then E, the range of a linear transformation is a vector space. Similarly, we say this one it is true. And last one, the set of all solutions of a homogeneous linear differential equation is the kernel of a linear transformation. This one is also true. In 31, define t from B2 to R2 by tb is equal b0, b1 for instance. If bt is equal 3 plus 5t plus 7t squared, then tb is equal 315. Part A, show that t is a linear transformation. So that's mean we want to show that if we have q and b in b2, then tq plus tb plus q, this one is equal tb plus tq. Also for any scalar c, we want to show that tcq is equal ctq. And by this 2, we show that the transformation is linear. So now let us starting here. So 31. For any p and q in B2, and let C be in R, let C in R. So now T P plus Q will be equal, so TB is equal B0, B1. If we have T P plus Q, so this will be P plus Q 0 and P plus Q 1. This is equal to P0 plus Q0. This one is P1 plus Q1. So this one is equal P0 B1 plus Q0 Q1. This is just is TP. This is also is TQ. So from here we show that TB plus TQ is equal TB plus TQ. Similarly, for TCB, this will be equal CB0 CB1. So this is equal to C multiplied by P0 P1, which is equal C. B0 B1, it is just TB. So by 1 and 2, the transformation is linear. So T is a linear transformation. Now for part B, find polynomial P in P2 that spans the kernel of T and describe the range of T. So let us do here part P. We know that for any quadratic polynomial for which Q0, we want to, for Q0 is equal to 0 and Q1 is equal to 0, both of them will be 0. It has the form, both of them will be in the kernel of T. So Q will be a multiple of Pt, which is T multiplied by T minus 1. Let us write this one here. So for any quadratic, polynomial Q for which Q0 is equal to 0 and Q1 is equal to 0 will be in kernel of T, because the kernel is, we say that the kernel is all the transformation that's transform the vectors into 0, 0. So if we have TB, it is given by B0, B1. To be in the kernel, B0 and B1 should be equal to 0. So now if we have a quadratic polynomial Q, for example, and we want the transformation to be Q0, Q1, both of them will be equal to 0. This Q must be in the form B of T is equal t multiplied by t minus 1. Because if we substitute here 0, we'll get this one is equal to 0. So b0 is equal 0. If we substitute here 1, we get 1 multiplied by 1 minus 1, 0. So both of them, q1 is equal to 0, or b0, b1, both of them will give us 0. So now if we have a vector x1 and x2 in R2, given any x1, x2 in R2, so b must be equal x1 plus x2 minus x1 t. So why we choose this one? Because for this one, if we substitute or if we find b0, this will give us, that means t is equal to 0. So b0 is equal x1. And b1 will be equal, this one will give us x1 plus x2 minus x1, so minus x1 with x1, so this will give us x2. So from here, the range of t is all of R2. In 32, define a linear transformation t from b2 to R2. By tb is equal b0, b0, find the polynomials b1 and b2 in b2 that span the kernel of t and describe the range of t. So first, here it is given that the kernel of t is span of p1 and p2. So kernel of t is equal span of p1, p2. So now for any quadratic polynomial q, for instance, if we have q0, it is equal to 0, this q will be in the kernel. Because if we substitute 0, we get it is equal to 0. So here we get the 0, that means it will be in the kernel. So will be in kernel of t. So for any quadratic polynomial q such that q0 is equal to 0, then q will be in the kernel. So q should be in the form q is equal at plus pt square. This is the general form for the quadratic polynomial. If we now substitute q0, we'll get this one 0, this one 0. So q0 is equal to 0, that means q will be in the kernel. So from here, if kernel of t is span of b1 and b2, that means we can choose t as b1, t squared as b2. So from here, thus p1t is equal to t and b2t is equal t squared. So from here, kernel of t is equal span of t1, t and t squared. Now let us describe the range of t. Now if we have a vector v is in the range of t, what does that mean? Then if we have a vector v inside the range of t, so let us write it here. If v is in the range of t, then it must be in the form v is equal a and a. So to be in the form a and a, that's mean the matrix, that's mean the vectors is in this form, that means it is the image of the polynomial bt is equal to a. We cannot find this form unless our polynomial is bt is equal to a. So let us write here also, if a vector of this form is the image of the polynomial b of t is equal to a in bt in b2. So that means the range is a and a. So thus the range of t is the vector a, where a is in R, which is a real number. So the vector to be in this form, the polynomial should be is equal to bt is equal a. That means when we transform this polynomial to make a transformation, this will give us a and a. For any polynomials in R2 or any polynomial in B2, if we take two elements, if we take a polynomial in B2, we do transformation, the result will be a vector in R2. So the polynomial should be in this form, and the range will be in this form, which is a where a is in R.